So you can ask. So here you can ask, in this description, where is the throat of the NS5 brain where the decoupled theory lives? So for that, one has to understand what string theory does on this C2 mod ZK orbifold. This is also known as the AK-1 ALD space. Usually when you have this situation, it's a good idea to study to explore possible deformations of this geometry. If you're just looking at the tip, it looks like this C2 mod ZK orbifold. So let's consider simply as an trivial case, which is k equals 2. The k equals 2 example.
What happens when you drop the 1?
Then you get the ALE space. Yeah. If k is equal to 1, you just get C2, but that from this point of view is a trivial case. Start at k equals 2. So if you look at the orbifold C2 mod Z2, it's just 4-dimensional Euclidean space identified with a reflection in all directions. This you can deform the geometry in a way that preserves all supersymmetries. It will be described by the line 1 to O minus 2 over pi rho over P1. So the space roughly can picture it like before you have this orbital singularity. After you resolve it, you replace it singularity by some sphere that has some size. This P1 has some size, call it T. And you can also introduce some B field, a flat B field, flux through the P1. So also B field with let's say with some B flux, flat B field, the B flux through the P1, call it little b. In some normalization, this little b is defined modulo 1. So shift the period shift the flux of the B field by some integral amount. It makes no difference. Okay, so if you study, now from the string theory worldsheet perspective, you might think that the C2 mod Z2 target space from the worldsheet point of view will simply be described by the orbifold CFT. The orbifold CFT is a perfectly good conformal filter from the worldsheet perspective. It has just the sector and the string spectrum will be discrete and perfectly reasonable, and nothing singular happens, and there will be no decoupled degree of freedom at the singularity. So that does not describe the throat near the NS5 ring. To understand what's going on there, let me say that so from the worldsheet the worldsheet perspective, this part of the target space will be described by some CFT, which has 4,4 superconformal symmetry. The small n equals 4 superconformal algebra. Now the moduli space of 4,4 superconformal theory in 2 dimensions, this worldsheet conformal field theory, is severely constrained. It's a quaternionic Kähler manifold. In fact, you might wonder how can this thing with the 2 moduli be quaternionic Kähler, which would require the moduli space have dimension that is multiple of 4. the answer to that is there are different places in the modular space that are related by some rotation that essentially had to do with the fact that this space is non-compact, and there's some isometry of the space that would lead to there's some isometry that acts that does not act on space in a way that does not die off at infinity, and this size modulus t will actually be replaced by a particular CFT of the sort labeled by some size t of the P1, and the flux of the flat B field through this P1 will actually correspond to a entire sphere in the modular space of this worldsheet theory that is rotated by the isometry. And the actual modular space of the actual moduli space of this CFT, if you restrict yourself to considering these kind of local normalizable deformations, turns out to be just S1 times R3 mod Z2. If I draw a picture, it basically looks like draw a picture that looks like this. So there's going to be this circle and some R3 direction, but if you just take S1 times R3 and multiply by the C2, that is going to be a reflection in R3 and also reflects on the circle. At the origin of the R3, it will leave two fixed points on the circle, which correspond to, let's say, B equals 0 and B equals 1/2. That's the structure of the modular space of this 4,4 superconformal theory. It has, if you start at the free orbital point, which you all know from the usual CFT description, if you just do the C2 mod C2 orbital, that corresponds to this point in modular space with, corresponding point with 1/2 unit of B field. There's another point in the modular space where you turn off the B field completely. Even though these 2 points are look the same in the modular space, the physics of the CFT is completely different. So this is a case where the modular space fails to capture the physics of this conformal field theory. Unlike usually if you play with the sigma model on Calabi-Yau manifold, all you talk about is modular space, and you think that captures a lot of physics. In this case, in this 4,4 theory, this modular space captures only a very small part of the physics. The claim, or at least the conjecture, which everyone believes, is that while this point in the modular space describes the free orbital theory, this other point describes a singular CFT. And this limit, as you move toward this point in the modular space, by the way, this is completely in the stringy regime, so it's invisible from the quadratic point of view. The CFT will develop a continuous spectrum, and you'll have an expected description that involves some linear dilettante and plus other stuff. And this is where the throat of the NS5 ring comes from. Now, this picture generalized to generally the C2 mod CK LE space. So to summarize, the point is that this 4,4 CFT that describes this LD part of the geometry of the 10-dimensional spacetime has a point in its modular space where a throat develops. And the spectrum of CFT is singular, in the sense that you develop a continuous spectrum.
Sorry. What was the string coupling doing in your TDP description?
The string coupling, you can, it's just to be anything. I mean, this is we're doing the weak coupling background, and now you can.
Maybe I should ask, before T-dualizing, if you didn't do the smearing, the string coupling went off to infinity.
Where? You mean?
If you put all the NS5 rings together, then there's a place in R equals 0 where the string coupling was infinite.
Let me see. that is true, but
does the smearing cut off that region somehow?
I don't think so, but it's a good question. So you're asking why is it that after doing the duality you just get constant string coupling? There must be a simple answer to that question, but somehow it's eluding me right now. Let me see. So. I don't have an intuitive explanation of that, but just have to. But there's some non-trivial H flux in the speckle. You have to be real careful in computing the tedialized geometry. But anyway, it's clear that for constant string coupling, this is a solution to string theory with all the right symmetries. Okay. So
sorry, one more question. If you dropped the 1, before doing the duality, the whole geometry, not just some part of it, describe the throat.
The throat is in a region where this superdramatic description is not really valid. So
let me do it before doing the duality first.
Yes.
Okay. Then if I just dropping the 1 describes the throat. Right. The throat is everything that is not flat space. Right. That's as you explained in the beginning of your lectures. The decoupling limit was taken by dropping the 1, basically.
Oh, no. Okay. I think maybe this actually is the resolution to the puzzle you raised earlier. Here, the setup is a little different. So initially, I'm not considering NS fibrine in just diameter Minkowski space. I've already come back by the circle to begin with. So you have to also take that circle to infinity. So there are. So this is. So I'm not starting with exactly the same setup.
I see. So actually, could you say what setup is starting with again, please?
The setup is you start with 6 number Minkowski in space. Well, it's just compact on the circle, and you have NS fibrine that are transfers to this circle and smeared on the circle.
Fine. So now, if I there's a certain region in this geometry where it becomes like just S1 times R3 times
Yes.
R6.
Yes.
Okay, and everything else I'm going to call the throat.
Everything else.
Once you start seeing this geometry deviating from that, I call that the throat.
Yeah.
Wouldn't I get the throat just by dropping the 1? Going deep down the throat is just dropping the 1.
No, you don't get the throat. You see, so indeed, in this case, the throat from this point of view is cut off because this goes like 1 over x as opposed to x squared, and you don't get the throat. The sphere shrinks.
I see. So there's finite. So the region over which it deviates from flat space is finite rather than infinite because of this smearing.
That's correct.
I see. So that, I think, as you say, explains the string.
Yeah. Now, this is actually a pretty. This is a pretty subtle picture. So we'll come back to this actually. Now, so an alternative way to define the Liouville string theory is to say that they'll be described by string theory on 10-dimensional space-time, which is R1,5 times this C2. It's a little misleading to write this. So I'll just call this the A k minus 1 LD space. But 1 is supposed to look at the limit in this of this LD space where the Cauchy CFT becomes singular, going to this point in the modular space. And let me just emphasize again, this is a common confusion. You might think this is a free overflow CFT, but it's not.
How do you know where one is supposed to look at this theory?
Where in the modular space?
Yes.
Well, every other place you have a non-singular Cauchy CFT with some discrete spectrum of normalizable states, and there's no throat.
But even before the NTU-CTP, you said that the throat was not there.
No, there's going to be some limit that's involved. Basically, let me see. There's going to be some limit involved in that where you adjust the size of the circle. So I don't have a clear way to justify from this side that you will get the same you'll get the same decoupled theory, but somehow we believe that if you do this, you end up with the same decoupled theory, the singularity of the L space. Okay, so from this point of view, if you so you can say either type 2A or type 2B. The way I defined it, I started with NS fiber and type 2A, but then after doing the T-duality, this will be turned into type 2B on this AK minus 1 LD space, and type 2B will be turned into, this was the 2, 0 Liouville string theory, this was 1, 1 Liouville string theory. So this turned into type 2A on this AK minus 1 LD space. Here,
sorry, but just to understand, when you did the T-duality, you got a smooth geometry. The only thing that you were unsure of was what that B was, right? Because it was like a Wilson.
No, after T-duality, you get a geometry with a ZK orbital singularity at the origin.
Oh, I see. You actually have it, right?
Yeah.
So you get a blow up of that.
You don't. You will get a blow up of that, as I just described now, if you separate these NS fibrins in the transverse R3 direction. In fact, if you resolve this LU space, you get basically a bunch of P1s that intersect. Let me just draw a picture like this. As I already mentioned, this corresponds to one way to do this is to spread these NS fibrins in transverse R3 direction. In the type 2A picture, you will have D2 branes, in rough D2 branes on these resolved P1s of this AK-1 LD space. They are massive particles from the 6-dimensional point of view. They are localized to the tip of this, near the tip of the LD space. And the mass goes to 0 if you shrink down this P1. So these have the interpretation wrapped D2 brane. This will be interpreted as doubly bosons in the 1, 6-dimensional super-Yang-Mills description. The resolution where you separate this NS fibrins before T-duality correspond to going to the Coulomb branch of this theory. Now, this 1 super-Yang-Mills is only a low-energy description. A priori, if you have some theory, so this Liouville string theory is supposed to be some kind of UE completion of this 1 super-Yang-Mills theory in 60. And if you look at the low-energy physics, you would expect it should be described by some, let's say, Wilsonian effective action of that of the super-Yang-Mills, but plus a bunch of higher dimensional operators constrained by 16 supersymmetries. Even if you have maximal supersymmetry in this case theory, you can still have infinitely many higher dimensional operators you can add to the theory, which are D terms. There are F terms, and which are very restricted, and then there are D terms, for which there are infinitely many, arbitrarily high dimension. And I would like to understand what they are. And that is part of our goal. And in this case, as I already mentioned, the low energy limit reduces to the 2,0 theory. And instead of these W bosons, you have, let's say, D3 branes wrapping this P1, giving rise to some strings that become tensionless in the going to the origin of the Coulomb branch of that theory. Okay. Now, let me give you yet another perspective on this. So you can consider actually, so before I said that the low string theory will be described by type 2 or type 2b string theory on R1,5 times the dilaton times this S3 with k units of H flux. That was the near horizon geometry of the NS5 brane. And so the strings, this gluons in this 1,1 super theory live kind of down the throat that's in the strong coupling region, but if you are kind of in the region of where phi goes to minus infinity, weak coupling, you still have some fundamental strings. So what do they look like in this gauge theory description? So the fundamental strings in this picture are going to correspond to instanton strings in the 60 gauge theory, in this 1,1 case. So you can, let's say, take some R4 and there's another R, and then there's time. You can take an instant solution in Yamio's theory in R4 and just extend that in the R direction and make this instant string. If the instant string, so going to the, in this picture here, you have this sphere, S3, and then you have this negative phi. Actually, let me show it the other direction. Phi, it's weak coupling to the right, strong coupling to the left. This is this region will be UV from the gauge theory perspective. So if you go into UV, that corresponds to this instant string shrinking to a very small size. See, this instant string, so in fact, you sort of know that if you have 6-dimensional gauge theory and make an instant string, this instant string, if the size modulus is the true modulus of the instanton, then you will know about the extra dimension because you can shrink it down to arbitrary small size or it can grow to arbitrary big size. If you shrink down to arbitrary small size, that will correspond to some weakly coupled fundamental string in this picture. And this instant grows to some very big size going to the IR, and that actually corresponds to the string become strongly coupled. And so that's the picture there. Okay, now we come to the question of so how do we cut off the strong coupling region? This is the double-scaled Liouville string theory of Gilian and Kutasov. So one would like to deform this space-time geometry in such a way that you want to cap off the linear dilaton R phi direction. From the NS5 brane point of view, we'll consider the following construction. So we'll still start with flat space, right like this. So the NS5 branes are extended in R1,5 direction, and the transverse R2 is a plane, there's another plane. So before the NS5 branes are stacked at the origin of the transverse R4, I'm now going to, they're still going to be on top of each other in this R2, but here I'm going to spread them out. Well, you can spread them out any way you want. These are, although these configurations preserve supersymmetry, the same set of supersymmetries, but I'll do that in such a way that these K NS5 branes are going to be spread out on a circle in this R2 and at equal distance from one another. just to have some symmetry, some zk symmetry that permutes these guys. So this size of the circle here, I'll call it R0. So spread the NS5 brane on a small circle of radius R0, and one considers the double scaling limit where you send R0 to 0 and the bulk string coupling to 0, while keeping the ratio G S over R0, call this G effective, to be finite. This is in alpha prime units, so alpha prime is set to 1 here. In string units. So this is a double scaling limit, and the claim is that there is going to be a decoupled theory living on that stack of NS5 branes still, and it'll be some kind of perturbative string. Well, if G effective is small, it'll be some kind of perturbative string theory whose effective string coupling is going to be the G effective. So let's understand this a bit better by inspecting. So we're going to focus on mostly on type 2b string theory from now. So we'll consider this this corresponds to the 1,1 Liouville string theory. So here, let's say we have a bigger picture with this NS5 branes spread out, say k equals 6 of them. You can have, let's say, you can stretch a D1 brane between these NS5 branes. This is a configuration that exists. This NS5, this first thing is D1. So the mass of this, the radius is R0. So the mass of the D1 goes like R0 over times the tension, GS times LS. The LS is set to 1. So this is 1 over G effective. I'm ignoring factors of order 1. And these are going to correspond to the W bosons. These are, again, the W bosons from the point of view of the 1 plus dimensional super Yang-Mills theory. So one expects that this double scaling limit to be describing, at least in the knowledge limit, the Coulomb branch of the 1,1 super Yang-Mills theory, and the G effective, the string coupling, is 1 over we map to 1 over the mass of the W boson. This is in the units set by the, I think I didn't say it earlier, but the 6-dimensional Yang-Mills has a coupling which has dimension length, and that will be identical with string length. And in units of G Yang-Mills, the effective coupling of the string theory will be 1 over the W boson mass. So the picture is the following. So we'll have the modular space, the Coulomb branch modular space, modular space of the 6-dimensional Yang-Mills theory. The 6-dimensional super Yang-Mills theory is the low-energy effective description, which you expect to be valid, to be useful on the Coulomb branch, provided that the W boson mass is not too big. So the usual kind of description where you just think of turning on the vevs, scalar vevs in this